it's time to talk about the relationship between the rate of a reaction and the concentration of the reactants. So that relationship that describes, or that relationship between the rate of a reaction and the concentration of the reactants can be described by something called the rate law. By the way, I am so sorry to keep bumping into my mic like that. I know it must be boring. Or not boring, but annoying. That's what I meant to say. Anyway, so rate law, right? It describes the relationship between the rate of a reaction and the concentration of the reactants. So let's just assume, for simplicity at this point, that we have a single reactant reaction, right? We have a chemical reaction in which one reactant, which we'll call A, decomposes into products, right? Now, the rate law for this reaction would be given by this equation here, where we have rate is equal to K times the concentration of A, remember that's moles per liter, right? Concentration of A to the nth power. So we know what concentration of A is, but we haven't talked about what K is and what N is. K is a term called the rate constant, which is simply a constant of proportionality between the rate and the concentration. And the power, right, the exponent up here that the concentration is raised to is called the reaction order, right? And so basically what this equation is telling us is that oftentimes the rate is proportional, the rate of the reaction is proportional to the concentration of the reactant raised to a power. So we have K, the rate constant, and N, the reaction order, and then of course this term here, A in brackets, that's just the concentration of the sole reactant of this chemical reaction, right? Now, there are three common values of N. There are three common orders of the reaction, and we're going to discuss all three of them. And so let's just say that N is equal to 0, right? N is equal to 0. This is called a zero-order reaction. And in a zero-order reaction, the reaction rate does not depend on how concentrated the reactant is. So you could have like a really, really, really concentrated reactant, right, like 50 moles per liter, something like that, or you could have something like 0.0000001 moles per liter of the reactant. It doesn't matter. It doesn't matter. Your rate is not going to change based on the concentration of the reactant. And so I think this is another opportunity to go to the whiteboard real quick. So we're talking about zero-order reactions. So I'm going to go back to the whiteboard. And so I need to do it on my software as well. What I'm going to do is I'm going to clear this out. Okay. And I'm going to get rid of you too. What the heck? Sorry, guys. All right. Just clear it out. Okay. So we're talking about zero-order reaction, right? And the rate law would be, for the zero-order reaction, would be rate is equal to K, the rate constant, times the concentration of A to the 0 power. Zero order means 0 is the power that the concentration is raised to. Now, we all know from mathematics that anything raised to the 0 power is simply 1. And so this equation becomes simplified down to rate is simply equal to K, right? The rate is equal to the rate constant. It doesn't matter what the concentration is, it's always the same rate, always the same speed of the reaction. And we'll discuss the factors that affect reaction rate in a later video. So I'm going to head back to the PowerPoint. So that was zero-order reaction, right? Now, what if, let's see. What if the value of N is 1, right? Then we have what's called a first order reaction in which the reaction rate is directly proportional to the concentration of A, right? So in other words, if the concentration of A goes up by a certain factor, the rate will go up by that same factor. As one goes up, the other one also goes up in a proportional linear fashion, right? So that's a first order reaction. Got some other messages in the chat. It says, sir, I know it is a little outdated, but can you use a whiteboard to teach because it will save you time and effort? Yeah, I mean, I could certainly give that a try. Thank you very much for your feedback. Okay, so that's the first order reaction, and then the next one that we're going to go over is the second order reaction. So that means if n equals 2, right? Second order reaction, that means the reaction rate is proportional to the concentration of that reactant squared, right? So that would be rate equals K times the concentration of A squared. Picture a little 2 right there. So zero order, first order, and second order reactions. So what do these sort of look like? Well, this is what they would look like in terms of a concentration versus time curve, right? So the concentration versus time curve shown in red, that would be for a zero order reaction. The blue one's for first order, and the green one is second order. So notice that no matter what value this concentration has, right, the value of this, or excuse me, the slope of this one, the zero order doesn't change. But for the first and second order, the slope of this curve actually does change depending on what your concentration is, right? So you can see here that the concentration sort of drops off quickly, you know, and then it starts to sort of slow down, right? Which makes sense because in the first order or second order reaction, you start out with, let's say, you know, you start out with a lot of your reactant, and then as it reacts to form products, you form less and less of it over time. Whoops. And then, so the rate is going to slow down, right? So now if we look at this, this is instead of concentration versus time, this is rate versus the concentration, right? So as can be predicted for a zero order reaction in which the rate is simply equal to the rate constant, because a to the 0 power sort of cancels out, right? It's just a flat line, right? Doesn't go up, doesn't go down. It's just a constant, right? And in the case of first order reaction, we have the rate is equal to K times the concentration to the first power, right? It's just a linear sort of relationship, right? Where if the concentration goes up, then the rate goes up by the same factor. Direct proportionality. Now, the second order, I'm not sure how, I'm guessing you guys are pretty good at mathematics, but like if you think about the curve represented by y equals x, and then you think about the curve like y equals x squared, right? Y equals x is just, you know, a straight line, right? And then y equals x squared is like a parabola, right? And so that's what we're looking at here. Hey, hope you enjoyed the video. If you'd like to watch the full video from which this clip was taken, click the box over there on the left. And if you'd like to watch my entire chemical kinetics playlist, click the box on the right. Thank you very much for watching, and take care.